Okay, class. Assalamualaikum and hi everybody. So today I'm going to continue from the previous lecture, which I already covered some part of the assembly language. If you remember, I asked you guys to go through on your own because that's how you learn about the assembly language because you have to do it practically by using the MySim85 software. Alright, so this is just a little bit of more information that you should know about the assembly language. Alright, so this is how the assembly language format. As you can see, the first item here, if you write the assembly programming code, so you can use a label where you can label the specific line where you can refer it to in your code. For example, you want to call it to go to the label, you can go back into the label. There are many functions of the label, but you have to know the first item that you can put in your programming in the programming line of your assembly language is the label. And then the second item is opcode, where it represent the operation that you want to perform on that line. And then the operand involved is the third item, and then the fourth item is the command, where you can put any comment to explain about the specific function of the line in the assembly language. All right, so there are few things that you have to take note, because if you miss this kind of items, you might get error when you try to compile it or you try to assemble it into the hex from the assembly language to the hex format. The first one is the colon, where you put it after the label, and then the second one is the space between opcode and operand. As you can see, you need to have a space. You cannot make it like just next to each other, else the compiler or the assembler will give you error when they try to compile it. You need to have at least a space between the opcode and also the operand. And then the other thing is, uh, in the operand, if you have two operands here, you need to divide it by having the comma. The same thing, guys. If you don't, you miss the comma, you'll get error. And finally, the semicolon. This is a must. If you miss it, you also will get the error message. All right. This is some of the assembler directive which you can use when you are writing the assembly language. The first one is the origin. For example, here this origin 200H, which is referring 2000 in hexadecimal. This means the next block of instructions should store in memory starting from this specific address. Let's say, if you have this, the processor or the AT will know that the instruction that they should refer to have to have to be from this specific memory location. And the other thing is the assembler directive. And the assembler directive means where you tell the assembler what to do. For example, specific memory, and here is to tell the assembler that this is the end of your code. And the line here is the equate. For example, in C programming, where you have different variables and you can assign the variables to specific value. So the same thing here. Here is you equate port A is equal to 80 in hexa. And also you can define the variables that you want to use in the assembler and in the assembly language. For an example here, dfb, the data is being initialized as a byte size. You can also initialize data as a word size, where you can do like this, dfw, and also define a storage area, where you reserve a specific number of memory for you. Okay, class, this is the flowchart on writing and also testing your code, your assembly code. So if you see at this flow diagram or flow chart, we start with the writing the program or the source code or the assembly language, and then we assemble it or we compile it, and first we will see whether there is any error or not. I mean, the example of error might be you spell the operand wrongly, or maybe you forget to put colon or semicolon, or you forgot to put space between the operand and also the what do you call it, the operand and also the opcode. All right, and then they will check whether there is an error or not. If there is an error, then you have to go through your code and you have to find the error. And if there is no error, the assembler or the compiler will generate the hex file for you, where the hex file is the file that you're going to download on the 8085 hardware. This is the file that can be can be understood or can be execute by the 8085. And then as you download the file on the 8085, mean you will check whether you are getting the expected result or not. I mean, you program 8085 to do certain function, and then you have to check whether the function that you expect is what you are getting. If you are not getting what you expect, then you have to go to what they call a process. We call it as a debug. Mean you have to go through your code and find which line or which part of your code that caused the error, and you have to find it and fix it. And then you have to repeat the process again, and then download into 8085 and then test it again. If you get whatever result that you expect, then that is the end of the process of writing a program for 8085. Okay, this is an example of adding between two number using A and B register. But the main purpose, sorry. So here is the example where you can use whatever features that we have discussed before. For example, here, I mean, it's the label, and here is where you equate or you assign this num1 equal to 55 hexa and num2 equal to 78 hexa, and this is just the adding process, just to show you how we can use all the features that we have discussed before. All right, and then here is wait. All right, so okay, this is if you see, for example, this instruction move move A to B. So this is the logical of the instruction, and this is the opcode number for the specific instruction, and also this is the size of the instruction, which is 1 byte, and t-state is the number of cycles involved to complete the instruction. Same thing goes here. I mean, this is the instruction, and this is the logical process that involve the instruction. This is the opcode number which represent this operation, and the size of the instruction is 3 byte, and this is the number of cycles that they need to complete this instruction LXI. Okay, class. And then for example, this is the code that can be understandable by human, and then when we compile it, the assembler will convert from the instruction that can be understandable by human into the code that can be understandable by the machine, which we call it as machine code or hex file. And then each hex file will be stored in the memory location. For example, here is the address of the memory, which is also in hexadecimal. As you can see, for this instruction, it takes around 3 bytes of size. That's why the address start here from 2000, and then the next instruction is stored in the address location of 2003, because one address location can store one byte of data. For example, here, I mean 31 is one byte, right? The 3 is 4 bit and 1 is 4 bit because this in hexadecimal, and 4 bit plus 4 bit is 8 bit is equal to 1 byte. So there are 3 bytes involved for LXI, and then move I is involve 2 bytes of instruction, as you can see, and that's why it started the address location that is store the instruction here start from 2003, and then the next instruction after this is being stored on the location 2005, which means the location 2003 and also 2004 is being used for the instructions. So in the machine part, they just look on this number, but for the human part, we are looking on the programming code, this assembly code. All right, this is just a little exercise where you can do. And yeah, this is how you can see the manual assembly. I mean, the same thing, the instruction here. I mean, you can see the machine code here. I mean, these are all the assembly code and it's being transformed into the machine code. Okay, what is assembler class? Assembler is a program that translates the source code, where the code that you are writing, the assembly code or the mnemonics, into binary code, which is the machine code. The machine code, this is the assembly code. In addition to translating mnemonics, the assembler performs various functions such as error checking and memory location. So while compiling, while the assembler is changing from the assembler code to the machine code or hex file, I mean it also done a few extra thing where they'll check if there is an error in your code. I mean an error such as you forgot the comma here, or you forgot the semicolon before you write the what they call comments, or you forgot to put the colon here. I mean those are example of error where the assembler will try to search for, I mean will check it, and if there's an error the assembler will let you know, then and you have to fix it. Until there is no error, then the assembler will successfully change from the assembly code to the hex code. And also the other thing is it will check the memory allocation so that the assembler knows where to put all these, what they call it, the where to assign each data to the memory, specific memory location. All right, this is the example. This is your assembly code, which you store it as .asm file, and then when you assemble it, or you mean or we can say you compile it, mean the compiler will normally will produce two files. The first one is the hex file and the second one is the listing file, where the extension of the listing file is .lst and the hex file extension is the .hex. Okay, this is just the example of the list file. I mean, this is not the file that you're going to send into 8085, but this is the file that where you can refer it. This is the direct translation of the assembly code into this hex code, where you can see, I mean, which hex code represent which assembly code that you write in your program. And then this is the example of hex file. This is the data that going to be downloaded into the 8085 hardware. As you can see, there are header here. I mean, like header means that there are files before you reach the beginning of the file you transfer here. The data byte program code. I mean, there are few header file which will explain what is this data all about. As you can see here, there's a byte count where tell you the number of data bytes in the records, so how many data, uh, the number of data bytes in the record, means record. And then okay, actually this is how the data being changed into the hex file. So they will be headed. There are a few added information here which will tell the 8085, where's the start of the file, and byte count, the address, and also the call type, which you can refer for that information here. All right, where we'll discuss about this one later. But that is the thing, the brief thing that you have to know. I mean, from your assembly code, it will be changed into the hex code. So as you can see here, I mean, normally you will connect the 8085 board to a PC through a serial port connection. For example, this one is using the RS 232 serial connection from a PC. After you mean complete writing your assembly code, or you complete writing your program in assembly language, then you compile it, then you get the hex file .hex file. The hex file will be downloaded into this 8085 development board, where you will not be using this board for the subject here. But this is the fundamental thing that you have to know, because if you go into the industry, I mean, if you involve in this like a board development project, so this is the step that you have to know, the procedure that you have to know after you done complete writing the program, and you have to connect the board to the PC and download the program into the development board. Normally, there will be a software provided for you to download the hex file into the development board. All right, so done for this part. Okay, class. Now we're going to cover about the introduction to input output devices. How the 8085 communicate with the input and also output. So this is the old style of connecting within the I/O and also the memory. So the recent processor, they have different way, but we need to know the method or the technique that being used by 8085 to communicate with these what I call it, input and output devices. So for 8085, they have two separate address spaces. The first one is this memory address space, means that they have a specific bus to connect the 8085 to the memory. Okay, as you have to recall, in my previous lecture I told you, right, the 8085 don't have this built-in memory, so you have to connect 8085 to a memory. So in this case here, we have to connect 8085 with two different memory. The first one is the 16-bit memory, which will be used as the memory where you're going to store the data, the instructions, or whatever, as the one that we have discussed before. Those memory will go into this memory, this memory which have 16-bit address space. And then the other one is this I/O, input and output, which have the 8-bit address space. So to communicate with the uh, I/O, normally 8085, they'll talk through this memory. Wait, let me, oops, wait. Okay, class. So just try to look for this drawing pen so that I can draw something. Okay, let's say this is your 8085 here. So you have, oops, okay, draw. Okay, let's say this is your 8085, and here is the memory where we connect it with this 8-bit address space. So this is I think this there's a IO memory here, and then here we have the either it can be input or it can be output device. So this device, they cannot communicate directly with the 8085. All of the communication will happen here through the address space. mean that's why we have two separate address. This is for the IO, and we have another one for the memory. All right, now what happened? Oops. Okay. Okay, let's go here. So, separate sets of instructions are used to access storage location in the memory address space of the processor and the I/O address space of the processor. So you have to use separate instruction to access the storage location, and there will be a specific instruction where you can access the I/O address space to communicate with the I/O peripherals or I/O devices. All external data transfer instructions are then the input port and output port access addresses in the memory space of the processor. So all of the data transfer that involve the memory will use the specific memory space, the address of the memory space. So the execution of this type of transfer, mean the transfer of data from 8085 to the memory, will force the control line of the IO and M. There are few control lines, like right, as we discussed before. So there is a specific IO slash memory control line will be forced to logic 0. So when you set the status line out IO slash M equal to 0, that means that the data transfer is happening from 8085 to the memory. If the IO slash M control line is equal to logic 1, that means the 8085 is sending the data to the IO memory or communicating with the IO. So it can be sending a data or accepting a data from the devices. All right, so this is the example of the two port. Okay, so this D07 is coming. I mean, if you see, the arrow is pointing toward the 8085, and this is the control signal that is controlled by 8085, and this is the connection where we connect it to the device or to the input or output peripherals. As you can see, class, mean the number of bit or the number of connection that we have here is 0 to 7, which means 8 bit, and we can have multiple devices connected here. Might be this be one device, input device, this one can be output device. So the process or the 85 will control which port that the 8085 want to communicate with. So let's say if this port is being activated, will be deactivated. So all the data will be taken from this specific port, which is controlled by the control signal from the 8085. And then the address input connections to the IO device provide a mechanism to select a particular 8-bit port from the ports within the device. That's what I mentioned before. I mean, there's a specific control signal that will be sent by the 85 to choose which port to communicate with. For example, the 8085 want to communicate with this port, then this port will be activated by this signal, and the data will be obtained from this port, and there's nothing happening from this port. And if the processor, the 8085 now want to access the second port, then the first port will be deactivated. As simple as that. I mean, there's a brief idea. And then this is the example of the decoding. Decoding means, for example, we have, let's say, 16 devices or 16 peripherals that we are connecting it to the 8085. So this is the decoder. I mean, this 4-bit can activate whichever peripherals or whichever devices that we want to communicate with, or the 8085 processor want to communicate with. I mean, by having this, for example, the 4-bit input is 0, 0, 0, that means the CS0 will be activated. If the input is 0, 0, 0, 1, then the second line here will be activated. It's just as simple as that. And then same goes if the processor want to write, because the example that we shown here is the processor is getting the data. That means the devices is writing the data or sending the data to the 8085. This is the example where the processor can send data to the peripherals, or might be can say to the output devices that being connected to the 8085. Same goes here, the control signal will be coming from the 8085, which will activate one port at a time. For example, this port is being activated by getting a control signal here, then all the data will be sent to, the data will also go to this port. This port is not being activated, so the data not going to be transferred here, so the data is just being transferred from the first port. Right, that is the memory.